The difference between a homogeneous and a heterogeneous reaction is that in a homogeneous reaction, you can't differentiate between the phases. So even if you put salt into water, it's still a homogeneous reaction. You can't actually see the difference between the salt and the water at the end, even though salt was a solid to start with. And once it goes into the liquid, then the particles dissociate, but it looks like one phase. A heterogeneous reaction, you need to distinctly see two different phases. They may even be both liquid, but you can see two different layers, like an oil and a water type of reaction. That would also be heterogeneous because you can see a difference. The most common heterogeneous reactions take place, or catalyzed reactions for us, are when you have a solid catalyst in an exhaust pipe, and then the gases flow over that, or sometimes in many chemical reactions like the Haber process, for example, you're going to have an iron oxide catalyst, which is a solid, and then the gases move over that. Will an increase in temperature increase the rates of both the endo and the exothermic reactions? Remember what an increase in temperature really means. It means an increase in kinetic energy. And if the kinetic energy increases, then you invariably are going to have faster movement of particles. That faster movement of particles does not mean that only hot particles move faster or only cold particles move faster. All particles move faster. Therefore, all particles are going to collide more. More collisions means more effective collisions, and therefore it's going to increase the rate of endo and exo reactions. An excess of magnesium is added to dilute hydrochloric acid at a temperature of 18 degrees, and the following spontaneous reaction occurs. So we've got magnesium, it's a solid, hydrochloric acid, which is an aqueous solution. We've got magnesium chloride, which is in solution, and hydrogen gas given off. They tell me that the delta H value is negative. That is clear that it is an exothermic reaction. They asked me what is a spontaneous reaction. A spontaneous reaction doesn't have to be an exothermic reaction, can be non-spontaneous as well. Spontaneous reaction simply means that I do not have to add additional energy to get the reaction to go. Explain why the rate of the reaction will gradually decrease. This is an important concept. As the reaction starts, I have got lots of magnesium surface area. I have also got lots of HCl concentration. In other words, lots of particles, lots of moles of HCl. When these two start to react with each other, I land up in a situation where the magnesium slowly gets less and the hydrochloric acid concentration gets less. So now there are less reactant particles available to collide. And as a result, the reaction rate is going to slow down. If I was going to draw a graph of that, I would land up with initially steep gradient, getting less and less and less until it levels out. At that point, you've got the reaction has reached what's called completion. In other words, I am not getting any more of the product being formed. Everything has stabilized. In terms of collision theory, explain what a change in temperature will have on the rate of the reaction. Explain what effect a change in temperature will have on the reaction. And we will find that the particles have got, and you have to explain it. So you need to say the following. You need to say more kinetic energy, because kinetic energy is linked to temperature, therefore more movement, therefore more collisions, therefore more effective collisions, and faster rate. This list is quite important because it comes up over and over again where they ask you to explain why something causes the reaction rate to go up. So the first thing you're going to say is, let's say, more surface area, more exposed particles, therefore more collisions, more effective collisions, faster rate. Or greater pressure. Greater pressure results in more particles coming close together to one another, and therefore more collisions, more effective collisions, faster rate. So these 3 points come up no matter what you're trying to point out. Increase in concentration means there are more moles of particle in the space, therefore there are more collisions. More effective collisions, faster rate. Those are just the answers. If we're looking at number 4, the decomposition of hydrogen peroxide can be accelerated by catalyst manganese dioxide. The peroxide rapidly decomposes into oxygen and water. The water is given off as steam because of the high heat of the reaction, and you've got hydrogen peroxide decomposing into oxygen and water. What is the function of the manganese dioxide? Refer to activation energy. What is important is that you now talk about the fact that it is a catalyst. That will obviously be worth a mark. A catalyst decreases the activation energy by changing the mechanism of the reaction, therefore speeds up the reaction. A graph is drawn, and we've got mass loss of hydrogen peroxide. So in other words, there's less and less and less mass of hydrogen peroxide, and against the time of the decomposition, and the time goes along. What does the horizontal section of the graph during the last 20 seconds? So in other words, they're interested in why has this gone flat. That means that there has been no further mass loss. We have reached what is called completion. Asks you to redraw the graph in your answer book with graph 1 on it, and then draw another graph of the mass loss on the same axis if manganese dioxide was omitted. If that happened, it would take much longer for completion to be reached. So we'd start in the same place, but we would end much, much later. So the big thing to show is that you reach that same point of completion. In other words, the same mass loss here on the graph but it takes much longer. So let's say this was 60, this would be, for argument's sake, 120 seconds. Then they say draw another graph. This time, mass loss if the peroxide solution was heated. So now we want to reach this completion point much sooner. So I'm going to come straight down like that, and that is my graph 3. Notice, for argument's sake, that that's 30 seconds. So with more heat, it goes faster, and what you've shown here is that without a catalyst, it goes slower. And they're the slightly neater answers of that. Notice, by the way, that all of them land up with the same completion point. In other words, that mass loss is constant. Doesn't matter which reaction you're dealing with, the end point is still going to be the same.